This recurrence equation is slightly different from the previous ones because in spite of the fact that this is a linear recurrence equation, there is a coefficient that is not constant here. It depends on n. And we will see now that this is going to introduce some important differences in the derivation of an equation for the generating function. Well, as usual, we're going to introduce the generating function defined like this, right? The ordinary generating function of the whole sequence, right? And we're going to proceed as we normally do. We multiply the whole equation by z to the n because n is the largest index. So we have this, right? 2 times an minus 1 z to the n plus 2 times an minus 2 z to the n. And now we sum over the range of valid indexes n. So what we have is the sum from n0 to infinity, 2, from n2 to infinity, and an z to the n is equal to 2 times the sum from 2 to infinity, an minus 1 z to the n, plus 2 times the sum from 2 to infinity, an minus 2 z to the n. All right? And now we are going to arrange this a little bit, right? Let's keep here this for a moment, right? So we just copy this. Well, actually, I'm going to do something is I'm going to write this from 0, right? From 0 to infinity. Okay, well, actually from 1 because 0 for 0, this is equal to 0. And the difference between this sum and this sum is the first term, so I have to subtract the first term to compensate. The first term is just 1 times a1 times z, and a1 is equal to 2e, so we have 2e times z here. All right, so that's what we have in this previous sum, and now we have this sum that we have to interpret. Then we have this here. There's a mismatch between the exponent and the index. We take out the factor z, so we just write here. So we put the factor z here and subtract 1 here, right? Now we have the same index, and then we change the index 1 unit down here and 1 unit up here. So we have the sum from n equal to 1 to infinity, an z to the n. And in this one here, we get a factor z squared up here, right? And again, we shift the indices and we have the sum from 0 to infinity, an z to the n. All right, this is just the generating function, okay? This one here is the generating function except a0, right? So this is fz minus a0, which is e, okay? And now we have this one here, which we have to interpret. This, if we didn't have this n here, that would be the generating function, the normal generating function, this one. But there's an n. How do we get an n here? Well, the easiest way is to take a derivative of the function f. If we take the derivative, okay, well, first, of course, the term n equal to 0 is a constant and the derivative makes it 0. So we have the sum from 1 to infinity, n an z n minus 1, right? Okay, right? Now, if we multiply this by z, then we have this, n z to the n, because this n compensates for this n minus 1 that we have there. And this is the sum that we have here. So actually, we can interpret this as z f prime c. So now we can write down the equation for f is z times f prime z minus 2ez is equal to 2z f z, right, minus 2z e, or 2ez, right, plus 2z squared fz. Okay, this and this cancel, right? And we put everything well, we factor out the f here, and then we have z f prime z is equal to 2 z times 1 plus z, right? 2z squared is 2z 1 plus z, and f of z. Fine, because the z cancels, right? And the equation we end up with is this one. F prime is equal to 2, 1 plus z f. Okay, what we get here is called a differential equation. This is a differential equation. And this is something that is probably you're not used to deal with. However, this one is very simple. All we have to do here is to divide by f. And then I have in the left-hand side f prime divided by f. And f prime divided by f is just the derivative of the logarithm of f. Okay? So the derivative of the logarithm of f is equal to 2, 1 plus z. Then calculating the primitive of this is straightforward. Is logarithm of f is equal to 1 plus z squared. Right? The derivative of this is just this one here. Plus, of course, a constant. Okay? How do we determine this constant? Well, we know something about f. If we calculate this f for z equal to 0, what we have is the logarithm of f of 0, right? And it's equal, if z is equal to 0, this is 1 plus c, right? But what is f of 0? Well, f of 0, if you go to the definition of the generating function, if you make z equal to 0, the only term that survives in this sum is the 0. So it's a0, okay? And a0 is e. So what we have here is, this term is log a0, which is log e, which is 1. So the equation we end up with is 1 is equal to 1 plus c, which makes c equal to 0. And then we have logarithm of f equal to 1 plus z squared, right? And eliminating from here f, or taking exponentials, what we have is this. This function is the generating function of our sequence, right? Another question is how to extract the coefficients from this, and this can be problematic, right? In a case like this, I mean, you have it. This is not a function that whose expansion is easy to figure out, right? So it's something that you have to apply more effort to. There is a technique, although this is beyond the course, right? This is a technique. Okay, you see here in the statement of the problem. It says find the generating function. It doesn't say that you calculate the sequence because it's complicated, as I said, right? There is a technique which once you know that the generating function, you are able to obtain at least asymptotic expressions for an when n goes to infinity, right? So you can get an expression here, which depends on n, and it provides a valid formula when n is large, right? And it's a very good approximation. And there are standard techniques to extract this information out of the form of this function here. But these are, of course, much beyond the scope of the course. So I'm going just to stop here. The point of this exercise is simply this, to illustrate that whenever, if you have recurrences with constant coefficients, then you end up with an algebraic equation for f, and then you can solve it in the same way as we have done in the previous exercises. But if there are coefficients that depend on n, then every time an n appears, it involves a derivative of the generating function. And you can imagine that if you have n squared instead of n, then you will have the second derivative of the generating function. And the equation, the resulting equation, after applying this technique, is a differential equation. It's no longer an equation, an ordinary equation, an algebraic equation, right? It's a differential equation. And if the order of the differential equation, meaning the largest derivative that appears here, is high, is 2 or beyond 2, then this can be very complicated to solve, right? So apart from this fact, Well, this is a good illustration of this peculiarity here, right?